Alright, let's open up to page 62. We're going to continue looking at domain today a little bit further with some functions, but we're going to step it up a little bit, and instead of looking at a graph to determine domain and dragging our pencil left and right, we're going to just look at an equation and try to figure out what is the domain. Okay, so a little bit more advanced today. We left off yesterday talking about how we can start to think about what the domain is, okay, if we don't have a graph. So on page 62, I know the graphs are at the top of the page, but just for today, at least for right now, pretend that they're not there. We looked at the rational function together and started to look at some values, like whether a value would give an answer or not. And I believe that we concluded that -2 was not a part of the domain, but -1 was. Did we do that one together yesterday? Okay, so we can start to pick and choose values to plug in, see what we would get out, but I don't know about you, I don't really feel like plugging in every single x value to test to see if it would work or not. Okay, we would be here forever because there's an infinite amount of x values. So we're just going to try this process for the remaining functions, but then we're going to start to talk about like what are some shortcuts or properties we can look for to help us determine the domain. So in terms of the square root one, let's just check to see if -4 is a part of the domain or is it not, and then the same thing with 9. So if we were to plug in -4, that would change to a 5 plus 4, which would be a 9. Good morning. We do have something. Thank you. Have a good day. So if we plug in -4, we would end up with a square root of 9, which would be 3. Okay. Let's go ahead and check 9. If we plug in 9, we'll get the square root of -4, which is what? Yeah?
2i.
It is 2i. Okay, if you're familiar with imaginary numbers, okay, you could say 2i. Since it's imaginary, you could also perhaps say undefined because it's not a real number that exists. Okay, so I would accept either one of those. But depending on your mathematical background, you may be familiar with the I or not. So what we're going to try to do is just compare whether -4 or 9 are a part of the domain. And yesterday we said our definition of domain were x values that produced or resulted in a y value. So notice how -4 did give us a y value, whereas 9 did not. So we can say x equals -4 is a part of the domain, but x equals 9 is not. Again, if we didn't have a graph, this would start to give us an idea about x values that would work and x values that would not. We would definitely have to check other values to get a bigger picture, okay, more accuracy, but again, I don't feel like checking every single value till we're blue in the face to see what would happen. Okay, but at least this is a start. Let's try the next one. If we plug in -11 into our cubed root, we'd have the cubed root of -8, which is what? Yeah? It is -2. Okay, so take a look at the difference. We said that the square root of a negative number was undefined or imaginary, but the cubed root of a negative number actually exists. So it's not just a root. You have to be careful about which root you're using. Is it a square root or a cubed root? Let's check out 5. If we plug in 5, we'll get the cubed root of +8, which in this case would be 2. So it looks like we got a y value out for both x values, so those x's must be a part of the domain. X equals -11 and x equals 5 are a part of the domain. Maybe we would want to check other values to see if we could figure one out that would not work, that would not give us a y value. But again, I don't feel like checking every single number. Okay, so this is just a start, but we're going to begin to think about, is there a better way? Okay, how can we determine quickly what the domain is and what the domain might not be? Okay, so let's check out 63. So we're going to start off with the rational functions. These were the fractions, okay, where we have a numerator and denominator. And we're going to take a look back on page 62 to see what happened here. If you took a look at the one we finished off with yesterday, okay, where we plugged in -2 and -1, what was special about that x value of -2? When we plugged it in, we said the value was undefined. What made that fraction undefined? Yeah.
The bottom, or the denominator was 0.
The denominator was 0. Okay, we know that we cannot divide by a fraction. Okay, we do not want to put the eggs in the bottom of a shopping cart. Okay, that analogy I used yesterday. So maybe that's a shortcut way to identify what the domain is. If we can figure out the numbers that don't work, that means that every other number would work. We can kind of use like reverse psychology a little bit, okay? If we can figure out what doesn't work, we then know what does work. So let's think about this. We know for a fraction, the denominator cannot equal 0. So if we can specifically figure out the numbers that would make the denominator 0, those are the only numbers that would not work. Okay, you can plug in any other number you want into that fraction and you would get a value, okay, except the ones that make the denominator 0. So the denominator can't be 0, which means the domain is all real numbers, okay, all those numbers, except those values, okay, that make the denominator 0. So when we come across a fraction, we're going to pay close attention to the denominator. Okay, what numbers could we plug in that would make the denominator 0? So let's check a look at number 1. Can you think about an x value that we could plug in that would somehow make the denominator 0? Yeah? 3. Okay, because that would make our first factor 0. So if this is 0 times something else would eventually be 0. Okay, so 3 is a number that would not work. It would make our fraction undefined. Is there another one? Yeah. 1. Okay, so x equals 3 and x equals 1 are x values that would not produce a y value. Okay, these are not a part of the domain. So if these are the only x's that do not work, that means all the other x's you could possibly think of would work. You could substitute them in and you would get an answer. So we're going to go ahead and represent that using our interval notation. Okay, we need to somehow show that we can go to negative infinity and positive infinity, okay, all real numbers, but we have to skip over 1 and 3 because those are the values that would make our fraction undefined. Can we start to think about what that might look like using our intervals, like parentheses, brackets, use? What do you think, Alex? Yeah.
Negative infinity, which with the parentheses, that's 1.
Okay.
And then u. Would it be 1 again?
Yep.
2, 3.
Uh-huh.
And then u.
Good.
3 to infinity.
Perfect. Okay. So if you think about a number line, okay, negative infinity to positive infinity, we can go all the way to the left, we can go all the way to the right, but we have to skip over 1 and 3 because those are the x values that we said would not work. So we can start at negative infinity, but we'd have to first skip over 1. Notice how that's where this interval ends and the next one begins. And we're using parentheses because we cannot include that value. But then, if you think about a number line, from negative infinity, we get to 1, we skip over it, Next, we would get to 3, and we have to skip over that one. So that's what's happening here. So we skip over 3, and then we can keep going towards infinity. So it's kind of a long interval, okay, because we have 3 of them to actually take into consideration. But we are skipping over only 2 numbers. Does that make sense? Can we see that? Okay. Let's go ahead and try the next one. Can we think about a number, maybe there's more than one, like the previous example, that would make the denominator equal 0? Go ahead, Jordan. 3. You see another one? Yeah.
-3.
-3. Good. Maybe you want to think about factoring. Okay, the previous example was factored for us. It has those nice little parentheses. If you factored x squared minus 9, that would be our difference of squares. That would be x plus 3 and x minus 3. Notice how you would get the same answers. Okay, so if these are the only numbers that would not work, because they would make our fraction undefined, we need to write our domain using our intervals. We can include every other number you want except those 2. So we're going to go from negative infinity to positive infinity and skip over -3 and +3. So very similar to the last example, we'll start at negative infinity. Our first x value would be -3 on our number line as we go from left to right. And then we'll go from -3 to +3, skip over 3, and then we'll go to infinity. Okay, again, kind of a long interval, but we're just showing how we can include every single number except those 2. Are we doing okay so far? We're just looking for the denominator. All right, let's try 3. Can we find a number that would not work in that denominator, that would make it 0? This one might not be as blatantly obvious as the previous 2 examples, but notice how if we can factor it, it might make that recognition of the x's a little bit easier for us. So let's try to practice just factoring that denominator. What technique might you want to use if you go through the various ones that we've went over this year so far? Is there GCF? No. It doesn't really fit the I am profile that I call it because that 2 out front. It's definitely not a difference of squares like the previous one. So what else do you want to try? Go, Jordan.
A times C.
There we go. A times C. So 2 times -3 would be -6. B is -5. 2 numbers that multiply to -6 but add a -5, yeah.
-6 and 1.
-6 and a +1. Okay, now depending on which technique you prefer to use, you can either do grouping, where you rewrite that -5x with those 2 terms, or you can do the divide and slide that we did earlier this year. Do we have a preference? We can do both. Divide and slide? Okay, so we'll do, this would be x minus 6, x plus 1, okay, those 2 numbers that we found, and then we're going to take that a value of 2 and divide those numbers. So we get x minus 3, since 6 over 2 simplified, but 1 over 2 does not simplify, so we'll slide the 2 in front of the x as a coefficient. All right, so if this is what the denominator factors as, what are the x values that would make the bottom 0? Yeah?
-1/2.
Okay, so that would make the second factor 0. And 3, that would make the first factor 0. Okay, so if the denominator is kind of complicated initially, okay, it might not be very quick to figure out what you could plug in to make it 0, try factoring. That way it's a little bit more obvious. So our domain would be every single other x value imaginable except those 2, because they would make the denominator 0. So we'll go from negative infinity to negative a half, negative a half to 3, and then 3 to infinity. Okay, make sure that you write your numbers in order, like on a number line. Okay, you cannot do negative infinity to 3 and then skip to negative a half. You have to make sure you follow that left to right progression. Are we doing okay with rationals? Yep, check out the denominator. Okay, let's go ahead and try square roots. So the first one we started off with today on page 62, we saw how if we plugged in negative 4, that value gave us an answer, but if we plugged in 9, that one did not. Okay, why did 9 not give us an answer? What happened with the square root? Go ahead, Alex. It was a negative result on the inside. Okay, so we know the inside of a square root cannot be negative. We know that fact, just like we know we can't divide by 0. So let's use that fact to our advantage. If the inside cannot be negative, what must the inside then be? If it's not negative, what else is it? Yeah. Positive or 0. Okay, so we have to check what numbers make the inside positive or 0. So we're going to set the inside, okay, set the inside amount or quantity, whatever it is. If it's positive, that means it's greater than 0. So we're going to have to set the inside greater than 0, but we also said that it could equal 0 because we can take the square root of 0. So we're going to set up a little inequality here. Okay, we want to show or represent when the inside is positive or 0. So take a look at our first one here. The inside is x plus 3. We know that that inside part has to be positive or 0. So we'll set it greater than or equal to 0. Can we solve for x? Yeah? Subtract the 3. Okay. So here's the domain for this square root. We can plug in any x value we want as long as it's greater than or equal to negative 3. Okay, this x is telling us the x's that would work, okay, that we can substitute in. The question is, what does that look like as an interval? Using brackets, parentheses, beginning point, ending point, if you can plug in anything you want as long as it's greater than negative 3 or equal to it, yeah.
Minus negative 3, comma, infinity.
Okay.
Brackets around the negative 3 and parentheses around infinity.
I like it. Okay, greater than or equal to negative 3. So negative 3 is kind of your beginning point, and you can go anything above that. So we'll go all the way up to infinity. Notice how if we can equal negative 3, we would have the bracket, but we'll never reach infinity, so we'll have that parenthesis. Okay, so there's our domain for this particular square root. Let's try the next one. So we know the inside of a square root cannot be negative, so we're going to check out to see when is it positive or equal to 0. So we want to solve for x. We can subtract the 4 and then divide the negative 2. What's going to happen? Good, Sam? The sign's going to flip. Okay, multiply or divide by a negative, you got to switch the sign. So this is telling us all the x values that we could plug in. We can plug in any x we want as long as it's less than or equal to 2. So the question is, how can we write that as an interval? What's the lowest number you could plug in? What's the highest number you can plug in? Brackets, parentheses, what's going on? Go ahead.
Negative infinity 2.
Okay.
Parentheses around infinity bracket.
Bracket 2 because we can equal it. Okay. Are we okay with that transition from inequality to interval? It's kind of advanced stuff here. I want you to try the next one. Find the domain. Which x values could we plug in? All right, so I got anything greater than or equal to negative a third, but the question is, what does that look like as an interval? What's the lowest number, highest number? Go ahead, yeah.
Would it be negative 1/3 with a bracket and
Okay.
then infinity with a parenthesis?
It would. How'd you do? Perfect. Okay, so we tackled fractions. That's when we just got to take a look at the denominator. When is that 0? Square roots. Okay, we got to check out the inside. But since square roots can be 0 or positive, we got to use that inequality. Okay, so it's always kind of revolving around this idea of 0, but the question is, what type of function are you working with? If it's a fraction, you got to check out the denominator. If it's a square root, you got to check out the inside. Okay, you got to keep those kind of separate or straight. The last function we took a look at was that cubed root. Okay, so if you take a look on page 62, it turns out if we plugged in a negative, we still got an answer. If we plugged in a positive, we still got an answer. If you take a look at the cubed root graph at the top of page 62, what did we say the domain was? If you dragged your pencil left or right, yeah. All real numbers, okay, so that kind of makes sense. We plugged in negatives, we plugged in positives, and we still were able to get an answer out for y. So the domain for a cubed root is all real numbers, except for something, and we'll check that one out in a little bit. So if you take a look at number 1, notice how it's a simple cubed root. You do not have to set the inside greater than or equal to 0. That's just for square roots, because we know we cannot take the square root of a negative. So since this is a cubed root, we know the domain is going to be all real numbers. If you look at 2, that's also a cubed root. Its domain will be all real numbers. What about 3? That's a cubed root. But can you think of a number that you could plug in and it would not work? Yeah.
Negative 1/2.
Why?
Because I'd give you a 0 on the bottom, hence making the whole thing like a 5.
There you go. Notice how the inside of this square root is a fraction. And we said previously we have to be kind of careful with fractions because the denominator might be 0. So if you have a simple cubed root, like nothing really complicated going on the inside, our domain is all real numbers. But the moment we might have a fraction, we need to be a little bit leery. So the domain is always all real numbers, except if there is a fraction on the inside. Okay, we have to check out when does that fraction, or when is that fraction undefined? Because if the fraction's undefined, the whole thing's undefined. Yeah.
So for fractions on the inside, would it only like not be all real numbers if there's an x in the denominator?
Would it only be all real numbers? So can you give me an example of what you're...
So like if it were just x minus 3 divided by 3 or something like that, would it still be all real numbers?
It would still be all real numbers because there's no x value that could change this to 0. That's a great question. Okay, do we understand what Adam was asking? Okay, since this is a number 3 and there's no variable attached to it, you cannot change it. So it will forever and always remain a 3. Okay, you just got to be careful with if there's an x. Good question. So what did you say our variable, our x value was, Alex, before? Negative 1/2. Okay, so our domain is usually all real numbers, but we cannot include this value. Okay, we have to skip over it. So kind of similar to the previous rational functions we did, okay, those fractions, we got to go from negative infinity to positive infinity, but skip over negative 1/2. Okay, so interval notation, we'll go from negative infinity, got to skip over negative 1/2, and then we'll go to positive infinity. So cubed roots aren't too bad, okay, because they're normally all real numbers. You just have to be careful about if there's a fraction, because we know some things can go wrong with fractions, okay, if the bottom is 0. How are we doing with domain? We didn't have a single graph for all those functions, and notice how we were able to determine the domain, okay, using some strategies or kind of shortcuts. Okay, We still have some time left in class, so I want you to try some of the examples from the homework just to get used to identifying the domains of different functions. Some of them have graphs, some of them don't, so it's going to be a good mixture of both of them. Okay, I'll be around if you need some help.